RC circuits consisting of resistors and capacitors are widely present in electronic devices and plays an important role in transmitting electrical signals in nerve cells. A capacitor can store energy, and when paired with a resistor in series, it regulates the charging or discharging rate, resulting in an exponential time dependence. Capacitor charging or discharging is not instant. It takes time. In a series connection with a resistor, the capacitor gradually charges through the resistor until the voltage across it matches the supply voltage.
The capacitor accumulates charge until its voltage matches the applied voltage, marking it fully charged. Charging rate depends on capacitance and circuit resistance. When voltage is applied to a capacitor, electrons move onto one plate while an equal number are drawn away from the other, creating a charge buildup. Let us consider that a fully discharged capacitor is connected to the circuit and the switch is open. At the circuit's initial state when time equals 0, the charge and current are both 0. Upon closing the switch, time begins at t equals 0, initiating the flow of current through both the capacitor and the resistor.
At time t is equal to 0, the potential difference across the capacitor is 0 and continues to be equal to 0 just after the time t is equal to 0. As time passes, the voltage on the capacitor increases until it reaches the desired volt while the current in the circuit decreases. The current flowing at this time is called the charging current, and it is calculated by using the Ohm's law. The formula for the current is as follows. Current is equal to the electromotive force of the cell divided by the resistance of the resistor.
The time constant during the charging of the capacitor is the time required to increase the charge on the capacitor by 37% of its final charge. It is the measure of how fast the capacitor can be charged.
Okay, let's now proceed to our problem solving. Find the maximum charging current through a 1000 microfarad capacitor connected in series with a 250 kilo ohm resistor and a 2.5 volt battery. Let's write down first our given. EMF is 2.5 volt, resistance is 250 kilo ohm with our maximum current missing. Substitute them in the formula I is equal to EMF divided by R. With the solution, our maximum current is 0.00001 ampere or 0.01 milliampere. For question number 2, a capacitor and resistor in series are connected to a battery with EMF is equal to 12 volt, capacitance of 8 microfarad, and resistance of 500 kilo ohm. For letter A, let's find the time constant of the RC circuit. First, let's write down our given with time constant missing. Use the formula for the time constant T is equal to R times C. Substitute the given values, then solve. Our answer for letter A is 4 seconds. For letter B, the maximum charge on the capacitor. Use the same given but with maximum charge missing. Substitute the given values to the derived formula of maximum charge is equal to the capacitance times EMF. Our answer for letter B is 0.000096 coulomb or 96 microcoulomb. For letter C, the charge on the capacitor 6 seconds after closing the switch. Use the formula charge is equal to the final charge times the quantity of 1 minus ruler raised to time over time constant. Apply the answers we had from previous questions, substitute, then solve. Then we get 74.89 microcoulomb when rounded off and 74.5 when not.